My name is Gordon McFadden. I'm an architect at Intel, and I'm going to talk to you today about what we've done with NGINX to enable some payload compression in NGINX, and we're going to introduce some technology and some software that we developed for this. Please feel free to ask any questions, just shout them out, and we'll get started. Okay, so I'm going to introduce the QuickAssist Technology hardware and software very briefly. I'm going to talk about the changes that we made to the NGINX core software, which is not very much. Some of the changes that we made to the QATzip software library, and then most importantly, I'll show you the results that we got from this. Okay. So Intel has produced some new hardware components that specialize in some offloadable technology. These exist in the current state in a chipset. It enables various types of encryption, including PKE and bulk encryption. It supports compression. And it comes in a bunch of different flavors. It's connected to the Intel processors via regular DMI link, and they are enumerated as PCI Express devices, which exist in the PCH. These are available both as PCHs on the motherboard and as plug-in cards. That makes it fairly simple from a software perspective to deploy and develop, but from a speed perspective, they exist on the PCH as well. For this, we're going to talk about the accelerated compression. And generally, the hardware has a capability to do a little over 100 gigabits a second of compression, measured in the uncompressed data. So this is the software stack. This is a simplified software stack because the entire software stack looked really terrible on this slide. We're connecting with the NGINX through the QATzip library and through the USDM library. The QATzip uses the standard QuickAssist user space library, down to the driver for some control stuff, and down to the hardware. So the USDM stands for user space DMA-able memory. If you have hardware working on memory, you kind of want to make sure it doesn't get paged out or moved in the event that a process is swapped out or terminates. And we have to operate on physical addresses. So we have a library that provides that. You can request, or the calling application can request a buffer. It gets a virtual address space that it can use to normally, but that's backed by physically contiguous memory that can be used directly by the hardware. In this particular implementation, the USDM library is using the huge pages available from the OS to provide memory. Okay, so what do we have to do to NGINX to make this work? When we did this, the first thing that we noticed was that as we expected, the deflate calls were chewing up a bunch of CPU cycles if the data compression was enabled. So the first thing that we did is we just replaced the calls to deflate init, deflate, and deflate end to equivalent calls, or we shimmed them into the QATzip library. And at initialization time, we allocated enough pin memory to deal with the data. And then as the incoming data was called in the deflate API, they were just moved into the pin buffers. And when all the data arrives, it's shipped to hardware, or if we fill up our pin buffers. So that gave us a decent amount of performance improvement. The time it takes to compress data in the hardware is quite a bit faster than it does in the cores. But we also found that there's a call to CRC32 that's called to calculate the CRC across the entire data set. And that call itself then became the most expensive piece of software from the perspective of the CPU utilization. And the hardware produces the CRC. So the next thing that we did is we modified it so that rather than calculating the CRC, it would just take it from the underlying calls. And that gave us a big chunk of performance improvement as well. So to support that, we took the call to CRC32 out of the function, NGINX HTTP gzip filter add data. And then in the filter deflate end, we just picked up the saved data. And then in the make file, we just added the pieces that we needed to make it link. A path to QATzip H, and then we just included the QAT and QATzip libraries during linking. And that is the only change that we had to do to NGINX. So while this is a proof of concept, the path to make this a full-on product or a patch is pretty straightforward. There's not a lot of extra that needs to be done if we wanted to keep the same data flow with the gzip filter, which is probably not a bad way to go. Okay. So what do we have to do to QATzip? So let me start by describing a little bit what QATzip is and why it was ideally suited for this. QATzip is a software library that provides access to the underlying acceleration device. But it also is designed to be a very straightforward API to use. You can just call QZ compress and QZ decompress without initializing any hardware or allocating any memory, and it will work. It was designed originally to support our efforts with big data, with enhancing Hadoop. And one of the requirements there was that some modifications, some deployments of Hadoop are multi-process, like NGINX, and some are multi-threaded, and it had to work seamlessly in both. And so we wrote that, we deployed it. It's very straightforward to use. The test program for it's about 40 or 50 lines of C code. You just call compress and decompress. If the hardware is available, it uses it, and if it doesn't, it uses software. So what do we have to do? We added the CRC32 pointer so we could expose that after the fact, after the call. And when we submit a job to the hardware, we just extract the CRC from the return codes and fill it in. If we have multiple calls to hardware, if we break a particular compression request up into multiple hardware calls, then we call CRC32 combine, which is part of the zlib API. It comes with the zlib library to combine the two CRCs. And this is also expensive, but it's about a third of expensive as calculating the entire CRC over the course of the whole data set. So it wasn't too bad. It's a little bit costly, and I'll show you in the results where we see that show up. But it was still better than not. It was still better than doing the CRC32 across the entire data set. Other than that, there's a straightforward application. Okay, so going into the performance results. So this was strictly designed to see if we could improve the performance of the platform that we have. We did this by running a couple of different tests with a couple of different data sets. So we took the front page of a couple of English language news sites, CNN Times of India and Shanghai Daily, and we did this because they came in a couple of different sizes, but they were all relatively compressible standard HTTP files. And then we wanted a larger one, so I just concatenated the three files together. So we used Apache Benchmark on a separate client platform, and we ran it as described there. We ran 32,000 iterations with a concurrency of 24. And we found it most useful if we were running 3 copies of Apache Bench simultaneously. I presume most people here are familiar with Apache Bench, right? Probably. Okay, so here's what we got. So we ran this in 3 phases. On your left, we ran it with no compression. In the center, we did it with software-enabled compression with the standard zlib API. And on the right, it's the same with the with QuickAssist-enabled compression. This was a fairly beefy platform. It's a 72-core 6150 at 2.7 gigahertz, and it has a 10 gigabit LAN to the client side. The client side was similarly configured, but it has a little bit less memory, I think. So what we see is that with the no compression, the time to complete for the CNN, or say for the concatenated file, the concatenation of the 3, was a little over 45 seconds. And that's network bound. We were getting 9.6 gigabits a second over the Ethernet, and that was it. With the other ones, it was sort of similar. When you enable compression, the completion time went down for both software and QuickAssist. Although with QuickAssist, you will, it takes much less time to compress, so your overall, entire end-to-end performance improves. And the cost of doing that compression is much less than doing it in software. You can see that the CPU usage, goes from 4% if you're not compressing it to 80% if you're running it through the standard deflate API, and like 13 or 14% using QuickAssist. And a good part of that 13 or 14% is the CRC32 combined. You can see that the concatenated and the times of India are a little bit higher, and that's because that was broken into 2 submissions to hardware, so we had to combine the CRCs. The other 2, the CNN and the Shanghai Daily, they were submitted as a single request to the hardware. And so we see a corresponding lower level of CPU utilization. So this is, for me, this is very interesting for a couple of points, in that you get better performance across the board no matter how you slice and dice it. This is, you get much faster throughput with a very modest penalty for the CPU. And it doesn't matter really what the size of the jobs was. If you look at the Shanghai Daily, the throughput times, the job completion times, were just about the same. But the CPU cost is not just about the same. It's a fairly significant difference, I think. We also ran the same identical test on a platform with a 40 gig, which I'll show you. And we got similar but different results. So this is on a platform with a 40 gigabit LAN. And I had asked our performance group to validate the data that I had collected, just to make sure that it wasn't invalid in some way. And they got very similar data. The CNN time gets much smaller because you're not I/O bound, and the rest of it kind of looks the same. The exact way that they used that was such that they got a lower CPU utilization, so all the numbers probably could have gotten a little bit lower, but it validates the same thing. Even in 40 gigabit network LANs, if you look at the completion time between no compression and QATzip, even on a 40 gigabit, you can get more traffic through compressed with QAT than you can without compressing it at all. And I think that's kind of the key takeaway. There's a fairly modest CPU cost and a fairly significant time to completion cost. Okay, are there any questions? Yes. I'm sorry? So the latency, yeah, we did collect those because Apache Bench collects those. The latency is obviously much better than software-based compression, and it's a little bit worse than no compression. There's obviously some cost to sending it to the hardware and retrieve the results. But at the same time, we used a hardware buffer of 256 kilobytes, and so that one is a single request. So there was, very, very, very modest, like, I don't have the numbers, but they're very, very small latencies to actually do the compression. Do you say in a multitask environment? Yeah. So we were running this with 72 NGINX processes, and they each had access to their own, the way the hardware works is they attach to a specific set of hardware ring counters, and so there's no contention on the submission retrieval from the hardware for each process. In terms of the actual underlying hardware itself, the underlying hardware itself is capable of, like I said, over 100 gigabits a second compression. And so if your outbound pipe is 40 gigabits, then you're not going to be in a situation where the underlying hardware becomes your bottleneck. You could, in a 100 gigabit platform, start bumping up against that. And if you had all other things, all of your other bottlenecks out of the way, then you might have to add some extra hardware to do the compression. Was there another question? Go ahead.
So you said that there was like 250K buffer. How is compared access time?
So we used 256 kilobyte buffers. We allocated those within the context memory of the NGINX, and we allocated those once at initialization time. And what happens is the NGINX provides us with 32 kilobytes of data at a time. We get a call, there's 32 kilobytes of data, and then later on we send back 4 kilobytes at a time. But those are all like copied into these hardware buffers, not hardware buffers, they're DMA-able buffers, while it's filling up. So until you get 256 kilobytes or until the job is done, all we're doing is just moving this data into a DMA-able memory, and then when we're done, we send it to hardware and we start sending back 4K at a time. Yes? So actually, that's a function in the zlib library itself. There's just a crc32_combine. And we validated that it produces correct CRCs. So the question was, how do we combine CRCs? So there is a function that does that. It's expensive because the combination is expensive. You have to provide 2 CRCs in the length, and then there's a vast amount of calculations that turn up. It's in the standard zlib library.
You don't need the source data from the first or either file.
No, you don't need the source data from either one.
How long is the CRC?
32 bits. It's a standard CRC 32. There was another one here.
Yeah. Is this technology available right now? Or do you have a lot now?
So yeah, the Mark, do you want to add that one? Is the technology available? So the hardware we've definitely, go ahead.
Yeah. It's available today. What he's demonstrating today is running on a platform that was released in July. It has this technology in PCH.
Yes. So these are, so the first one, the availability, go ahead.
Yeah, so in terms of those that were like the skewing toward the processor,
So, and in terms of the upstreaming driver, this uses the out-of-tree driver. The upstream driver is for kernel-only implementations. And at this point, we stage things into the distros as best we can. And this uses the out-of-tree driver, which is available on 01.org. It's downloadable, both the driver and the QAT. The QATzip is probably a week away. And so it's built from that. Okay, so I'm out of time. If there's one more, I'll take it and take the penalty. Yes. I'm sorry? Any which features? I'm not sure. Okay, well, thanks everybody. My clock ran out, so I appreciate you listening. And enjoy the afternoon. Thank you.